Okay, welcome everyone. How many people voted in person today? Yes. Wait just a few minutes for some other people to come back from the polls. I want to get to finally one of the main summits or capstone results of this course this week, namely Ratner's theorem and its application to the Oppenheim conjecture, which is of interest in its own right, and that I'll try to put in context of Lie groups and homogeneous spaces as we go. So I'm going to start today with some applications of mixing. So let me remind you what our most general mixing statement looks like in the homogeneous setting. We have this very nice version, which is what's often used in applications. If we let X be gamma mod G, where G is a simple Lie group and gamma is a lattice, which of course just means the volume of X is finite. And H contained in G is any closed subgroup. It doesn't have to be a Lie group, or I mean, it is a Lie group. It could be, for example, a discrete group. It could even be a cyclic group. Then the theorem that we sketched the proof of last time, the Hall-Moore theorem, says that the action of H on gamma mod G is mixing. And what this means is that if Hn goes to infinity in H, meaning it leaves every compact set, and A and B contained in X are measurable sets. I'm just going to say it in a slightly more geometric way this time. Then the measure of HNA intersect B tends to the measure of A times the measure of B if we normalize so that the measure of X itself is equal to 1. Okay, so last time I discussed how mixing can be used to prove some equidistribution results, and I want to put those results in context by discussing a very classical question, which is called the Gauss circle problem. So I see a lot of people with their videos off today. If you're willing to turn on your video, that would be great, because I'm going to ask some questions that would be nice to get just like a sort of a wave from the audience if they know what I'm talking about or not. So let me ask you to wave if you know what the Gauss circle problem is. Wave in front of your screen. I only see one hand. There's, seriously. Okay. Well, so Tina, tell us what the Gauss circle problem is.
I didn't raise hand.
Oh, you didn't? Okay. Did somebody who didn't have their video on raise their hand? Okay.
Yeah, the Gauss circle problem is you have a circle centered at the origin of radius r. Find how many lattice points there are, integer lattice points there are inside of the circle.
Right, very good. So, and it's usually phrased for R2, the first interesting case. So the classical Gauss circle problem is we have the integer lattice C2 contained in R2. And all we do is we look at a big ball around the origin of radius r. And within this ball, we have a big piece, a big finite piece of the integer lattice. And we let nr be the number of points in the intersection between Z2 and the ball around the origin of radius r. And the problem is what is n of r. Now, actually, that's not the precise problem. Let's work towards the precise problem. So first, who can give me a guess for what n of r should be, at least approximately? Somebody other than Bingka.
Squared?
Sorry?
Pi r squared, like the area of the circle?
Sure, who's saying that? I'm sorry, let me get on speaker view. There we go. Okay, thanks, John. Yeah, and why?
Because each point is roughly in a box of area 1. Each lattice point is roughly in a box of area 1.
Excellent. So the answer begins like this. N of r equals pi r squared. And in fact, that's the leading term. That's a good approximation up to ratios when r is large. And the proof of this is not hard. You just tile the entire plane by squares. And if a square, actually, I probably should have taken my squares to be centered at the integers. It doesn't matter too much. If a square lies entirely inside of the circle, then let's associate, if you like, to each square. Let me center the squares. I should have done that to begin with. Okay, so here's my lattice. Here's my lattice. And we choose a Dirichlet fundamental domain. That is, we consider the origin to be the capital of a small nation state, and it gets to govern everyone closest to it. And so we put a square, a unit square around each lattice point. And then if a state is entirely contained in this big region, then of course its capital is. And if a state is outside of this region, then of course its capital doesn't contribute to the count. So if you believe that the number of squares that are entirely contained in the region is a good approximation to the area of the region, then you would get this estimate. And where does the error come from? The error comes from the squares that meet the boundary. So they're not entirely inside the region and they're not entirely outside. And you could have a square that contributes something to the area, and yes, good, its center is inside, but then this point has been a little bit overcounted because we added a 1, and the area it's contributing to the inside of the circle is not 1. It's smaller than 1. On the other hand, there might also be a square whose capital is outside the circle, and nevertheless, it also contributes to the area of the whole region. And so there's an error term. How big is the error term? Just roughly speaking, what's a good bound on the size of the errors coming from the perimeter of the circle? Someone else?
Like 2 pi, the circumference of the circle.
Okay, that's good, but the circumference of the circle is not 2 pi.
Okay, 2 pi r, 2 pi.
Great. Yes. So the point is that the area of all of the squares that meet the circle is bounded by the area of, roughly speaking, a unit neighborhood of the circle. So there's an error term, but the error term is on the order of r. So the main term comes from the area of the ball, and then the error comes from the perimeter. So let's call that the length of the boundary of the ball. Okay, good. And so what is the Gauss circle problem? The Gauss circle problem is to improve the error term. So the improve the error term. And now, if you are a probabilist or a physicist, you know what the error term is, because you have, roughly speaking, R boxes around the perimeter. And then for each box, you can ask, is the capital in or is the capital out? And that's like a bunch of coin flips. And if you believe those coin flips are independent, then half should be in and half should be out, and up to a small fluctuation, which depends on the number of coin flips. So when you flip n coins, you expect about half of them to come up heads, but even more, you expect to be the count to be exactly n over 2 plus an error that's on the size of roughly square root of n. That's what the central limit theorem says. So we have R coin flips. So hopefully there's a lot of cancellation here, and this error goes down to R to the 1/2. And so the conjecture, and this is what I would call the Gauss circle problem, is that O of R can be replaced by O of R to the 1/2 plus epsilon, meaning that for every epsilon greater than 0, there's a constant, so the error is bounded by R to the 1/2 plus epsilon times that constant. And by the way, there's some beautiful work of Hardy and Littlewood that showed that this is best possible. In fact, they even showed that R to the 1/2 is wrong. So that you could get close to a half, but you can't expect to hit it on the nose. So that's the Gauss circle problem. And it's in some sense, the study of the error term is interesting as a mathematical challenge, but in some sense, getting the main term is really, the sort of the main impact of the theorem, that you can count the number of integer points in a region as being approximately equal to the area of the region or its volume in higher dimensional spaces. And various conditions on the boundary will ensure that there's a reasonable error term. And the existence of a good error term here, it depends on the circle being such a special and symmetric curve. If you were to draw a more random smooth curve in the plane, you might not get this error term. If you were, on the other hand, if you were to do conics, you would get something reasonable, but the main term would almost always be right. As long as you're looking at a region where the length of the boundary is much less than the area of the region, the main term will be correct. So the main term being correct is a very general statement. So now, what I want to do is explain how mixing allows you to solve the circle problem in hyperbolic space. So rather than trying to attribute this to someone's name, I'm just going to call it the hyperbolic circle problem. So what should we change in our picture here? Well, I like the ball of radius r, but I'm going to take that ball inside of hyperbolic space. So I'm going to work in the hyperbolic plane. And then I need an analog of the lattice. And the hyperbolic plane is not a group. So what's a good substitute for the lattice? Well, it's suggested by the word lattice. So we let G be SL2R, and this contains a lattice gamma that is a discrete subgroup with finite covolume. So we let X be the quotient space, gamma mod H. Might even imagine this as a compact hyperbolic surface. And now inside of H2, we take some point. There's no canonical base point. And we take the ball of radius r in the hyperbolic metric. Okay, so that's a good beginning of the setup. And now what shall we take for our lattice? What we can do is we pick a point Q downstairs on X, and then we look at the preimages of Q upstairs. So Q tilde looks like this. It's some sort of discrete set spread out through the hyperbolic plane. And it's obtained by simply taking one lift of Q, which I'll call Q, sorry, Q tilde is one particular preimage of Q. And then my red set is all of the translates of that particular lift by the action of gamma. That's the fiber of the quotient map. And notice that in the case of the plane, if we had taken the quotient of the R2 by Z2, we'd have a very similar picture. We'd have the torus, we pick the origin on the torus, and then its preimage is the integer lattice upstairs. So this is a good substitute for our previous discussion. And now, what's n of r? N of r is the number of points in the intersection between gamma q tilde and the ball around 0 radius r. So let's carry out the same proof. So first, we choose a fundamental domain. And again, we can use this Dirichlet construction by taking for each point upstairs the convex set of points that are closer to it than to any other point in the orbit of q tilde. And that tile is compact because the quotient gamma mod h is compact. And then some of these tiles lie inside the ball, some of them lie outside. And we have the same natural guess for what this number should be. It should be equal to the volume of the ball around P of radius r. And of course, P can be any point. So this is really just a function of r. It's the same for all points in hyperbolic space. We could write down the formula, but I'm going to keep it more conceptual. This is the n log of pi r squared. But then we're counting really the number of tiles. So we should divide by the area of each tile. And the area of each tile is just the area of the quotient Riemann surface. Or I'll call that the volume. I'll make this area since we're doing 2 dimensions. Divided by the area of x. Okay, and then there's going to be an error term. Okay, now let's try to make this a little bit explicit. So somebody who hasn't spoken yet today, tell me just very roughly, what is the area of a large ball of radius r in hyperbolic space? Just grosso modo. Don't need a formula, just like, how does it feel to you? Does it grow rapidly? Does it grow slowly? Is it pi r squared? Okay, I'm going to do something I rarely do, which is just call on people, but to make this civil, if you don't want to answer, just say pass. But I encourage you to answer. Guesses are welcome. So how about Ben Low? Do you have an idea?
Yeah, like exponentially.
So what does exponentially mean?
So like e to the r, I think, or
yeah, that's right. And in fact, that's right. So the area of this ball is approximately e to the r. So our guess is it's roughly speaking, and in fact, it's asymptotic to e to the r times a constant, which we won't worry about. Constant might even be 1. So we get e to the r divided by the area of x. Maybe I'll put the constant here just in case. And then we're going to get an error term, which is the length of the boundary of this ball. So the next thing I want to know is what can we say about the length of the boundary of the ball of radius r? In other words, what about the length of the circle of radius r? So somebody else want to speculate on the approximate length of a circle of radius r in hyperbolic space? How about Mary? Do you have a guess for what this might be?
I don't think I do right now, sorry.
Okay, no problem. How about Matthew?
I don't either.
Okay, so let's think about this. You have a ball and it's growing exponentially fast. That means when you increase the radius by 1, the area inside the ball approximately doubles. But the area that you add is proportional to the length of the boundary. So when you add the area of the boundary to the area of the ball, it doubles the area of the ball. So what is roughly the length of the boundary? Anyone?
Is it also exponential?
It's also exponential. Yeah, exactly. So this is this beautiful fact that, in fact, if you were to take a horror ball, we made this estimate before. Actually, I should say in any region in hyperbolic space, the area of the region is bounded by a constant times the length of the boundary. So the boundary has to be very long for the area to be big. So this error term is also on the order of e to the r. And now we see this is a disaster because our error term is on the same size as our main term. Okay, so just crudely following the argument that works in the Euclidean plane, we don't even get the main term. We haven't even proved that the main term is correct. And again, the issue is, how are the tiles that meet the boundary situated relative to the boundary? Are they sort of 50% in, 50% out? And now that makes a big difference because the area of the tiles meeting the boundary is almost the same as the area of the tiles inside the region. Okay, so this is a very important thing to understand about hyperbolic space. If you have a big island in hyperbolic space, no matter how big it is, and in fact, no matter what shape it is, most people get to live on the beach. The area of a unit neighborhood of the boundary is comparable to the area of the whole island. That's an amazing thing about hyperbolic space that's very different from Euclidean space. And so we need to somehow invoke some kind of randomness to even get the main term here. But we have a source of randomness. That's what mixing is about. Mixing says that as you apply a group element to a set, it becomes uniformly distributed. It becomes sort of randomized. And one thing you can prove using this theorem, as I sketched last time, is the following theorem, that on any finite area, hyperbolic surface, x gamma on H2, circles are uniformly distributed. And that means that if you have a continuous function on x, say with compact support, then the average of f over the circle around a point of radius r converges to the average over x of the same function as r goes to infinity. And indeed, once you have a good averaging over circles, it's just a formality to conclude that the same thing is true for balls. So I could actually say circles and balls, because averaging over a ball can be done by first averaging over each circle of constant radius in the ball, and then averaging over the totality of those. So one can actually, by the same argument, you can conclude that the average over the ball of radius r of f converges to the average of f. And so what you do is you take your point P and you push it down onto your Riemann surface, and then you take your point Q and you say, oh, well, wait a second, this has to do with with functions. So I'm going to replace Q by a little bump function like this. So I choose a function f such that the integral of f is 1, and f is supported very close to Q. Okay, so the integral of f is 1, and f equals 0 outside a small ball around Q. Around Q of radius little r small. And now I apply this theorem to the ball around P. So I start enlarging the ball around P, and it starts to go over the surface many times. So you have to understand this, what this average means. When the ball crosses the same point on the surface many times, it becomes immersed when the radius is large enough. And a good way to say what that means is that you just lift P to a point upstairs, and you lift f to a function upstairs. And then you could really say that this is the average of the lifted function over the ball around P of radius r, now where P is in the upper half plane, and the ball is as well. But what you see is that this bump function now has support at each point of Q, and its average over this ball is then counting the number of points inside, the number of occurrences of Q inside this ball. And so that's very close to giving you our desired bound. And now you might say, well, wait a second, isn't there an error term still? And there is, but you see the error now has to do with the radius of the support of this ball. We took Q when we smeared it out a little bit to radius r. And what that means, it's sort of like shrinking the fundamental domain to minuscule size. So that means when we take r, big R, and we add little r to it, then we get an overcount. And if we subtract little r from it, we get an undercount. But adding or subtracting a small constant changes this exponential by a small multiplicative factor. So we apply this averaging theorem with some r, and then we let r go to 0, and we get the desired conclusion. And so let me just write that down as a theorem, now that we see what the conundrum is. So the counting theorem for hyperbolic space says n of r, which is the number of points in gamma q tilde, intersect the ball around P of radius r, is asymptotic to this ratio, the area of a ball of radius r divided by x. And what that means is that if we call this function, let's call this a of r. After all, it's just the area of this ball up to a constant. What this means is that n of r over a of r tends to 1. And this whole thing here is roughly of size e to the r. Okay, so now you might say, very good. So the first term was harder to get, but we got it in the end. What about the error term? So what could you possibly hope for the error term? Well, the simplest thing is to pray that you can at least get an error term that's also exponential, but at a slower rate. And that would be really great, because that would then rapidly converge to the correct answer. And in fact, you can get an error of the size, let me write it this way, e to the 1 minus epsilon times the radius r, for some epsilon greater than 0. But in general, this epsilon depends on your Riemann surface x. And if you trace through the proof, you see that at the end of the day, what we'd have to know is how fast does the exponential flow mix? And to go from the qualitative argument that we use to prove this guy to an actual estimate is pretty difficult. If you think about how this estimate worked, it turned on the fact that the horocycle flow was ergodic. Remember, our proof strategy for mixing goes like this. First, prove the geodesic flow is ergodic, then the horocycle flow is ergodic, then the geodesic flow is mixing. So in the proof that the geodesic flow is mixing, you use ergodicity of the horocycle flow. And how do you use it? You use von Neumann's theorem, which says, well, if you have an ergodic thing, then the ergodic averages converge. And the ergodic theorem does not give you a rate. So you would have to go back and investigate what the rate is for convergence of ergodic averages for the horocycle flow. So that can be done, but it takes us considerably deeper into the geometry of X, and it involves things like eigenfunctions for the Laplacian on X. Okay, so that's an application of this abstract mixing theorem, and it shows two things. First, the theorem is very powerful in the sense that you can it neatly finesses the main difficulty in hyperbolic circle problems. But it doesn't have enough content as it stands to give you the error term. So it's very good at giving you the first term and giving you the desired qualitative behavior. Okay, so let me give you another example of the application of mixing. Similar to this statement here, that the circles and balls are uniformly distributed. So sometimes Riemann surfaces have cusps. Let's suppose we're in that situation. So X is H mod gamma, and it's finite area, but not compact. And that's equivalent to saying X has at least one cusp. So now we have a new geometric object to average over we didn't have before. So before, on a compact Riemann surface, the most obvious and symmetric shape we could draw on the circle, on the space, was a circle. But here, because we have a cusp, there's a new shape we can draw, which is a closed horocycle. So remember, this is not a circle. It has geodesic curvature 1. And in fact, around the cusp, there's a whole family of horocycles. And you should think of these as somehow renormalized circles where the center of the circle has gone out to the cusp. And so if we think in those terms, the center is infinitely far away, so the radius is infinite. So the radius is not a good way to describe these horocycles. A good way to describe them is by their length. So we'll call this H of L if its length in the hyperbolic metric is equal to L. And in fact, the lengths of these horocycles, like the perimeter of a circle, they increase exponentially fast, in the sense that if we take two horocycles that are distance t apart, then, and this is an easy calculation, their lengths are related by a factor of e to the t. So the length of this circle is e to the t times the length of that circle. Indeed, here's a prime example. Suppose gamma is SL2Z. Then we have the transformation z goes to z plus 1 in our group. And a fundamental domain for a neighborhood of the cusp is just the region between the vertical lines through 0 and 1. And now if we're at a particular height y, well, the hyperbolic metric is dz over y. And this horizontal line has the property that this point, the initial point, is identified with the endpoint by this element of the fundamental group. So this descends to a closed horocycle on the modular surface, which is this 2, 3 infinity orbifold, this cusp at infinity. And which horocycle is it? Well, that's easy. We just integrate the hyperbolic metric along this this line has Euclidean length 1. We've scaled by 1 over y, so its length is 1 over y. So this is actually the lift upstairs of h of 1 over y. And now, if you wanted to make this horocycle longer, you could take a parallel to it, which would move you farther away from the cusp. Remember, the cusp is up here. So you would multiply y by a factor. You multiply y by, say, y times e to the t, e to the minus t. And then the hyperbolic distance from here to here is just e to the minus t, because the integral from e to the minus t to 1 of dy over y, that's just the integral of log between 1 and e to the minus t, which is equal to t. So this hyperbolic distance is t, and the length of the horocycle down here is 1 over y, as we just computed, so it's y times e to the t. It multiplies by e to the t. Okay, so it's quite easy to understand these horocycles. And then the theorem is that on any finite area hyperbolic x, horocycles, by which I mean closed horocycles, circles and balls are uniformly distributed. And what that means is that if we do have a cusp, then we can take the average of f over the horocycle of length L, and that will converge as L goes to infinity to the average over the whole surface. Okay, so let me give you the idea of the proof. I did this very quickly for circles last time, so let me say it just a little more slowly this time. So the way you prove, so first let me draw the picture a little bit more clearly. So what happens is, you have these horocycles, they're getting longer and longer, and eventually they're forced to cross themselves on the surface. And then they have to cross themselves more and more and more. Also, they come back and visit the cusp, although they don't go out and converge to it. So h of L for log L is some very complicated curve immersed in the surface. But there's a simple way to keep it from being immersed, which is that we work in the unit tangent bundle. And then at each point here, you also have a vector, and these vectors are never tangent to one another, are never equal unless you've come back to the origin, the beginning of this closed horocycle. So these horocycles remained embedded in the unit tangent bundle. And now we want to apply mixing. So what we do is we need to take a set of positive measure A. And so we take, say, our horocycle of length 1, and then we take a little band about it of some small length epsilon. And now we have to lift it to the unit tangent bundle. And what I'd like to do is lift it by taking vectors which point outward from the horocycle, but that won't be positive measure. I have to choose an open set in the unit tangent bundle over any given point. So instead of doing this, I allow the vectors to be orthogonal to within an angle of epsilon. So that's my set A, and it's sitting not inside X, but inside the unit tangent bundle. Okay, and now what happens when I start applying the geodesic flow? So what happens is that if I take a point that's on the horocycle and I flow orthogonally, then after time t, I get to h e to the t. Now, what if I took a point that was, or it was orthogonal to these foliation by horocycles, but it was in this band rather than right here? Well, then I would get to a point that's in an epsilon band around the horocycle of length e to the t. So the vector is orthogonal to the horocycle, after you flowed by time t, remain in a band around the horocycle of length e to the t. So that's looking pretty good. And now there's a little calculation you have to make, which is what happens in hyperbolic space if you leave at angle epsilon instead of at strictly orthogonal to this horocycle. But what happens is you start to get more and more nearly orthogonal. And you end up also very close to the horocycle of length h e to the t. And in fact, as t goes to infinity, you become more and more nearly orthogonal to that horocycle. Okay, so the point is that this small band, suitably lifted to the unit tangent bundle, has the property that when you apply the geodesic flow, you end up in a small band around h e to the t. So that this picture that I'm drawing is the geodesic flow for time t applied to A. And now we take some other set B, and it's this set B lives downstairs on the Riemann surface, and we lift it to the unit tangent bundle by just taking all of the vectors that lie over this set B. So we take its full preimage in the unit tangent bundle. And now by mixing, GT of A intersect B has measure that tends to the measure of A times the measure of B. On the other hand, what is this set actually measuring? After we flowed by time t, we have this narrow band around a long horocycle, which is now very complicated on our surface. But it passes through B many times, and the proportion of the horocycle which passes through B is just this quantity divided by the measure of A. And that tends to the measure of B. And so at least if we thicken the horocycle slightly, then the averaging over the thickened horocycle becomes uniformly distributed. In fact, it can integrate the indicator functions of sets on the sphere. So you might worry a little bit about this thickening, but remember at the end of the day, we're averaging continuous functions. So if you take a continuous function and you change the value of x slightly, the continuous function only moves a little. So averaging it over a band is very close to averaging it over the core curve of that band, which is the horocycle of large length L. Okay, so that's the idea of the proof using mixing of the geodesic flow, that horocycles become uniformly distributed on X. Okay, so finally, let me give an application to this. So here's a nice problem. Choose a random point. Well, let me say it this way. Choose a random elliptic curve or complex torus. E equals C mod random. How can you do this? Well, we know that the space of elliptic curves is coextensive with the space of lattices. So this elliptic curve is determined by its lattice. However, the lattice is not quite uniquely determined by the elliptic curve. So the way one gets around this is we observe that E can always be written as the quotient of C by a standard lattice, C plus tau Z, where tau is in the upper half plane. And let's call that E tau, and that E tau is isomorphic to E sigma if and only if sigma is in the SL2Z orbit of tau. That's just amounts to a change of basis for this lattice and then rescaling, which doesn't change the elliptic curve. So a random elliptic curve is really the same thing as an equivalence class in the quotient of the upper half plane by the action of SL2Z, which is our nice 2,3 infinity orbifold. So I'm asking you to choose a point at random in this orbifold. Now, one way to do that would be to pick a fundamental domain for the action of SL2Z. For example, the region between the lines of the vertical lines through the points x equal plus or minus a half and the circle of radius 1. This is the standard fundamental domain for the action of SL2Z. And this has finite area, so by some process, you could try to pick a point at random with respect to area here. And that's not too hard, but it's also not quite obvious because we have to take the average with respect to hyperbolic area. And also, you have this curved boundary here. It's kind of a pain. So here's a different way to choose an elliptic curve at random. So let me just erase this background and write down the answer. The answer is choose epsilon small and then choose x in 0, 1 at random. And then set b equal to c modulo z plus z times tau, which I'm going to take to be I epsilon plus x. And the smaller epsilon gets, the closer this will be to being a truly random elliptic curve. And the picture is very simple now. To choose a random elliptic curve, you take the lattice generated by 0, 1, and one other vector. And what's the other vector? Well, you draw a line at very small height through I epsilon, and then you pick a point at random on this line between 0 and 1. So in other words, you pick a point x in the interval from 0 to 1, and then you take tau to be up here. And these two vectors, 0, 1 and 0 tau, those are the generators for your lattice. Now you might say, that's ridiculous. That's not a typical lattice. A typical lattice, how am I ever going to get anything close to the square torus this way? I've chosen two vectors that are very close to each other. Doesn't that mean that my elliptic curve somehow, its fundamental domain, looks like a very long parallelogram? But you see, these are not very good generators for the lattice because usually you can shorten the vector 0, 1 by subtracting off a multiple of the vector 0 tau. That would, for example, in this case, replace it with a vector that looks like this, pointing in the opposite direction. And since x is bigger between 0 and 1, this will be less than 1 in length. And so you can do that over and over again until you get a vector going horizontally that's rather less than this one, but then you can start shortening this vector. And so on and so on. So this is not a good basis for your lattice. In fact, in any lattice, you can find a basis where the two basis vectors are as close, have a smaller angle between them as you like. That's just a bad choice of basis. If you take the Z2 lattice, you can take a vector that looks like this and then another vector that looks like this, and they'll give this terrible looking parallelogram even though there exists a square basis. So in fact, this does give a random elliptic curve. And why does it give a random elliptic curve? Well, it's because all that we've done is we've taken this tau somewhere along this line. I'm just drawing the same line again, but normalizing so it goes between -1/2 and 1/2 along this line in the upper half plane. And what is this line? It's a closed horocycle because -1/2 is identified with +1/2 by translation by 1. And in fact, it's a parallel of this horocycle here. This is just HL, where L is very long. And long horocycles become uniformly distributed on the modular surface by this theorem, and therefore this gives a random lattice. Okay, so that is sort of a complement to the theorem of Hedlund. Hedlund says when you have a finite volume, when you have a compact hyperbolic manifold, every horocycle is dense. That's not true when you have a cusp. When you have a cusp, you have closed horocycles. But this result, which is fairly easy consequence of mixing, says that those horocycles become denser and denser as they get longer and longer. In fact, even better, they become uniformly distributed. Okay, so this result suggests that there should be a corresponding result in the case of closed surfaces. And what would it say? We don't have closed horocycles. Well, what it would say is that instead of averaging along a closed horocycle, we just average along a long horocycle. So what if it doesn't close? Maybe if we average F over just a very long horocycle, it will converge to its average over X. In other words, maybe the orbits of the horocycle flow are uniformly distributed. And in fact, that is a theorem. So the first theorem, which was proved by Furstenberg, is, and now let me use the terminology we've used before, but not recently in ergodic theory. The horocycle flow on a compact Riemann surface is uniquely ergodic. Remember, what that means is that there's only one invariant measure, and it has a very concrete consequence for the flow itself. This means that if we take a continuous function on our surface and we take the average, and in fact, even on the unit tangent bundle of our surface, and we take the average from 0 to t of F at the horocycle flow for time S applied to some vector X that we choose however we want, ds, that this average converges to the average over T1 of X of F uniformly and for all X. So it's a very strong condition, and it's stronger than Hedlund's theorem. Hedlund's theorem says this horocycle orbit is dense in the unit tangent bundle. Well, that's pretty obvious. If it's going to know the average of F, it has to investigate all of the space. But this says not only does the horocycle go everywhere, but the amount of time it spends in a given region is proportional to the area of its region. Okay, so I don't think that there's time between now and the last few days of this course at the beginning of December to prove this theorem. So I'll refer you to the notes for it. But I think that this theorem starts to make it seem plausible. So if closed horocycles are uniformly distributed, why not just ordinary horocycles per se? And that's what Furstenberg proved. Okay, so let's now, just as a kind of a review, let's step back and make a little scorecard for the geodesic flow and the horocycle flow. Because we proved a lot of theorems about these, and some of them show these are the same, and some of them show they're different. And Ratner's theorem is going to be about the ways things like the horocycle flow are better behaved than the geodesic flow. So let's review what we know about how they're similar and how they're different. So the first thing we proved about the horocycle flow, and let's say this is on X compact, or on its unit tangent bundle, on the unit tangent bundle of a compact surface. Well, the geodesic flow is ergodic. And also the horocycle flow is ergodic. In fact, those are both instances of the Howe-Moore theorem. This corresponds to the subgroup N, this to the subgroup A. These are two non-compact subgroups of our friend G, which is SL2R. And even better, they're mixing. They randomize. Okay, now what about, what could we say about, say, closed orbits of these flows? Well, the geodesic flow has lots of closed orbits. And that's because the every homotopy class of loop on the surface is represented by a loop whose length is as short as possible. If the homotopy class is non-trivial, that loop will be a geodesic. Or to put it differently, it's because if we've written X as H on gamma, then the elements of gamma correspond to the fundamental group of X. And the hyperbolic elements of gamma correspond to closed geodesics. And to be more precise, every homotopy class, every free homotopy class of loop, let me call it delta, is represented, it's homotopic to a unique geodesic. And if we orient this, then this inherits a corresponding orientation. And so in fact, these closed orbits correspond to, topologically, conjugacy classes in the fundamental group, as long as we remove the trivial conjugacy class. And of course, there's infinitely many of those on any surface. What about the horocycle flow? Well, of course, there are no closed horocycles on a compact surface. And the reason is that when you have a horocycle, once you have a horocycle, you can construct parallel horocycles by just pushing towards the center of the horocycle, and these get shorter and shorter and shorter at an exponential rate. So if you had a closed horocycle somewhere on your surface, we draw it here, then you would have to be able to make it arbitrarily short. And yet it's supposed to represent a non-trivial homotopy class. So it would have to leave every compact set, and that contradicts compactness of your surface. In fact, it shows the only way you can have a closed horocycle is by having a cusp. So on a compact surface, there are no closed horocycles. In fact, something even better is true. The horocycle flow is minimal. That is, every horocycle is dense. And this is dense not just on X, but in the unit tangent bundle. And of course, that's completely wrong here, because these closed orbits are not dense at all. And then we have something even better, which is in fact the horocycle flow is uniquely ergodic. That's the theorem of Thurstonberg that we just mentioned. That says that every orbit of the horocycle flow is uniformly distributed. And again, that's wildly false for the geodesic flow. And another way to say this is there's only one invariant measure for the horocycle flow, namely the standard Liouville measure on the unit tangent bundle of x. But for the geodesic flow, there's lots of invariant measures. For example, you can put an invariant measure on every closed orbit. But in fact, there's a vast space of invariant measures, which we haven't really seen yet, and would be natural to discuss when we get closer to Mossberg rigidity. But let's just say there's a vast set of ergodic invariant measures for the geodesic flow. And over here, there's only one. That's what unique ergodicity means. And finally, there's an invariant which we haven't discussed at all in this course, but I will give you a very quick introduction to. So let me say this invariant first for a map from a measure space to itself. Or there's also a topological notion here. So what we do is we take our measure space and we cut it up into a couple of pieces. And then whenever we have a point, x, we have its orbit, t of x, t squared of x, t cubed of x, etc. It goes marching around in our space. So the points of x give rise to what I'll call a language. In other words, they give a subset of the infinite strings on ABC. So it's a set of infinite collections of triples of letters indexed by the natural numbers. So for example, this particular x I wrote down, it gives the word B, A, B, C, and then A, and then it jumps back into, actually I didn't write where it jumps. Who knows? It keeps on going like this. Okay, so from a dynamical system plus a partition of the space, we get this language, which I'll call L. And now we can look at the number of words in L of length n. And we're expecting that to grow exponentially. So we can take the logarithm of this, and then we can divide by n. And this quantity, if the number of letters in the language grows like e to the delta n, then this quantity will converge to n. And so the limit here, as n goes to infinity, and of course you would have to discuss whether or not this exists. In fact, it does, although you may need to keep refining the partition to get a good invariant, is called the entropy of the dynamical system T. The entropy. And this is all related to information theory. Let me just say, roughly speaking, if you're observing just the letters associated to a point, the entropy tells you how much information you gain by looking at the orbit of the point. As you sort of get a more and more accurate picture of who X is by seeing more and more of its itinerary. And this is how much information you gain per iteration of T. In any case, it turns out that the geodesic flow has positive entropy, which means roughly it has this butterfly effect. A small change in the initial conditions doubles after a certain amount of time. And then that change doubles again. And so, you can't predict the weather 100 days from now. You can only predict it 10 days out. The horocycle flow, on the other hand, has zero entropy. Which means that you can do very good prediction of where the horocycle will go in a large amount of time, just knowing the initial position to within a small error. So it's much more predictable. And the reason here is that you should think of nearby geodesics as diverging exponentially fast, but nearby horocycles as diverging sort of polynomially fast. So I don't know if these pictures look different. This should be like the graph of y equals x squared. This should be like the graph of y equals e to the x. And so there's very different behaviors on these two sides. And indeed, this is sort of a fundamental division in dynamics itself. In dynamics, there are sort of fast dynamical systems. These are sometimes called hyperbolic. And they tend to have all of these features. Now, these dynamical systems, there's no standard name for them, but I'm going to call them unipotent. And the reason I like to call them unipotent is because this subgroup N has the property that its matrices are almost the identity matrix. Their eigenvalues are all 1, and a matrix with that property is said to be unipotent. Moreover, the terminology unipotent will be what we use in Ratner's theorem. And in Ratner's theorem, we'll describe a whole class of dynamical systems that enjoys all of the good features of the horocycle flow. And the existence of this class was suspected but not proved until the middle 1990s. Okay, so just one last remark. If you wanted an example of a dynamical system to keep in mind that's a toy model for the geodesic flow, one thing you might take in mind as a toy model, for this type of dynamical system is x goes to 2x mod 1. The doubling map on the circle. And it has all of these properties. It's ergodic, it's mixing, but it also has lots of periodic points. It has lots of invariant measures because it has lots of periodic points, and it has positive entropy. As a point starts doubling, if you just tell me if it's in the top or bottom half of the circle, that's like reading off the digits in the binary expansion of x. So after seeing 10 iterates of x, I know x to 10 decimal places. I've got an enormous amount of information about x by observing its behavior. What's a toy model over here? It's our favorite dynamical system. X goes to x plus alpha on the circle, the irrational rotation. So we proved that this is ergodic. Of course, it has no periodic points. Every orbit is dense. In fact, it's uniquely ergodic. We proved that. And it's not hard to prove it has zero entropy. But one thing that's different between this and the horocycle flow is it's not mixing. It doesn't mix at all, but it's sort of a forerunner to these more rigid unipotent flows. These unipotent flows are mixing, but it takes them a long time to mix compared to what happens here. Okay, so that was a little introduction to this. So let's step back and see a sort of dichotomy of dynamical systems on homogeneous spaces. Okay, so what I'd like to do is proceed now to the formulation of Ratner's theorem, which will be a general which will be the general setting for that captures all these good features of a horocycle flow. And I have enough time to just state it, so let me state it. This is the theorem of Ratner. So let's let G be a connected Lie group. And one thing I want to point out is there's no assumption of semi-simplicity. And this is a very easy theorem to remember. You don't have to know any Lie theory to formulate the group, or very little. Let's let gamma be a lattice in G. And then we need our horocycle flow. And so that's given by U contained in G, which is a closed subgroup generated by unipotent elements. And this is the only hypothesis that requires some thought. So the way to think about unipotent elements is that if U in U, of course, if this is inside of GLN R, maybe our group is given by matrices. This matrix is unipotent if and only if U minus the identity is nilpotent, which is the same thing as saying U minus the identity to the n is 0 for some n, which is the same thing as saying that you can write U as 1, 1, 1, 1, 0, and then something up here in some basis. And so, for example, all the elements of n are unipotent, and so U n itself is obviously generated by unipotent, because every element is unipotent. However, there are other groups that are generated by unipotence. For example, SL2R is generated by unipotence, even though it has lots of elements that are not unipotent, like diagonal elements. And the reason it's generated by unipotence is that you can write this group G, well, let me not call it G, you can write this as n times n transpose times n. You can write every element of SL2R as a product of upper and lower triangular matrices. And all of these are unipotent, so this is generated by unipotence. And so it qualifies for membership in the group in the subgroups that will work, where Ratner's theorem will work. Okay, now that you know what unipotent is, I'm going to erase, well, I guess I'll leave this up, but I'll say a word about how you say this more abstractly. What if your group is not inside of GLNR? What if it's not given to you as a group of matrices? How do you know what the unipotent elements are? Well, one thing you always have is the adjoint representation of your group into the general linear group of the Lie algebra of G. And that gives you a matrix or a linear transformation associated to any element of the group. And then you can ask that that transformation is unipotent. And that's the real hypothesis here. So people who are real sticklers for terminology will say add unipotent here. But when your group is given to you as a matrix group, it just means this. It's generated by upper triangular matrices and elements that are conjugate to upper triangular matrices with ones on the diagonal, or elements whose eigenvalues are all 1. Okay, so then here's the conclusion. The first conclusion is I can tell you what the closure is of an orbit of U applied to any element of the homogeneous space X mod G mod gamma. So for all X in gamma mod G, there exists a closed subgroup H contained in G such that the closure of this orbit is equal to the orbit under H. In other words, when you apply this unipotent group to X and then take the closure, you just get the orbit of X under a bigger group. And that orbit is already closed. And this orbit, XH, is closed and a finite volume. What does that mean that it's a finite volume? It means that if we want to figure out what this orbit really looks like, it's a homogeneous space for H, but we have to figure out what the stabilizer of X is. So XH is isomorphic to gamma H, mod H, where gamma H is the stabilizer, and the stabilizer comes from elements of gamma that happen to interact correctly with H. It turns out that that's just X inverse gamma X intersect H. And then the statement that it's a finite volume is that gamma H is a lattice in H. So this should have finite volume. So in other words, the closure of every X orbit has something to do with a lattice, and it has a beautiful homogeneous geometric structure. It's not fractal in the slightest. To the contrary, it's as simple as possible. And the second part of the statement says that all U invariant ergodic measures on gamma mod T arise as in A. You see the H measure on this quotient space, H mod gamma H, that's finite. That gives a finite measure on XH. And of course, it's U invariant because it's H invariant. Oh, I should have said here, as you could guess, U is contained in H. So the orbit closures are, so the way people put this briefly is they say all orbit closures and ergodic measures are geometric. And that means that they're supported on a submanifold of gamma mod G, and that submanifold is a finite volume homogeneous space. That's what this, the more detailed statement I've written down in A gives you. Okay, so I'm over time, but let me just finish by pointing out the prime example that we've seen of this already. If G is our favorite Lie group, SL2R, gamma is some lattice in G, and U contained in G, we might as well take this to be equal to N. This is our favorite unipotent group, 1 star 0, 1. Then what does part A say? Then part A says that Xn bar, there's two possibilities. It's either just equal to Xn, or it's equal to Xh for some bigger h. But it turns out the only reasonable bigger h that it can be is G itself. So it's equal to Xn, or it's equal to Xg. And what this says is every orbit of the horocycle flow is closed or dense. So in fact, this is Hedlund's theorem from the 1930s, and Ratner's theorem is a vast generalization of that result. Okay, so I'll develop this picture in more detail next time, and then we'll apply it to the study of quadratic forms and the proof of the Oppenheim conjecture.